Okay, welcome back. I think it's better now. So we're gonna start. I'm not sure who's still not here. Zinedine is not here. Okay. All right. We will start. I hope they're coming back. Okay. So on the long question, we have a compass is used to determine the poles of a magnet. The compass is placed in the different position around the magnet, right? Around the magnet is shown below. The dark arrow indicates the north pole of the compass. So this is north for the black one here, and that's north, right? So we know north, like poles, what do? They attract. Like poles, they repel, and unlike poles, they attract. So the north pole is pointing towards an unlike pole. So if this is north, therefore X is south. So our answer is X is south. So from here, please don't mind the numbering here. Originally in the question paper, it was question 9, so I changed it to question number 2. So just ignore the numbering there. All right, so this becomes 2.2. So the answer here is south. So the answer would be south. Zinedine wanted to ask something, but unfortunately he's not back yet. So we'll continue. We'll answer him when he comes back. Okay, let's move on to the next one. The next question says, at which position, 1 or 2, will the compass experience the strongest magnetic force? Give a reason for the answer. Give a reason for the answer. All right. At which position, 1 or 2, will the compass experience the strongest magnetic force? Give a reason for the answer. So you check towards the poles. That's where you have got the strongest magnetic force. So the answer would be position 1. The answer is position 1, right? So you're just double checking on the memo there, right? Position 1. Magnetic field is strongest at the poles of a magnet, right? There is negative marking here. It means if your answer is wrong, your reason is also wrong. So that's what we call negative marking. So checking on that one, what do we have here? The question says, what is the, choose the position and give a reason for the answer. So it's 2 marks. So the answer is position 1. Why? Because the magnetic field is strongest at the poles. So that's the answer there. Yes, Zinedine, you're back. You had a question on, which question was this? It's on 2.2. Huh?
2.1. I asked, how is it south?
Oh, how is it south? 2.2. Right. The reason is the black part here is north. Right?
Okay.
And we know like poles repel and unlike poles attract. So this part is black here, it's north. So we know north will be attracted to an opposite pole. So X becomes the opposite of north because the black part we are told here on the statement here. The dark arrow indicates the north pole of the compass. So this is north, therefore north must be attracted to south. So therefore X is south.
Okay.
Yes. So the answer is south, not north. Otherwise, if it's north, then it must point away because like poles repel. Okay. Next one. So we did 2.3. We're now on 2.4. What is the direction of the magnetic field? Choose from north to south or from south to north. Right. So as you can see, this is north and this is south. So it means the magnetic field lines are moving towards south. So it means Y must be north and X is south. So it moves from north to south. North to south. So the correct answer is north to south. Right, checking there on the memo, we've got your north to south for 2.4, north to south. Right, okay, we move on to the next one. The next one, it says, give one term for each of the following descriptions. The point in the northern hemisphere where the rotation of the axis of the Earth meets the surface. right? Rotation of the earth, that should be geographical north. So the answer there is the geographic north pole, all right?
Do we
Also,
have to
you
say
can say true north, because when we use the compass, we basically, the direction that we get, we're using the geographic north. So it's your geographic north pole there. Right, next one.
okay? So
Uh, yes,
if we just wrote North Pole,
come again.
if we just wrote the North Pole,
North Pole. Remember, there are two North Poles. There's a magnetic north and there's a geographic north. You have to specify. So just
oh,
North Pole, are you talking about the magnetic North Pole or you're talking about the geographic North Pole? All right, so that one you're going to lose a mark because we don't know whether you're talking about geographic or magnetic. Clear?
yes.
Okay, next one, 2.5.2. The point where the magnetic field lines of the Earth enters the Earth. The point where the magnetic field lines of the Earth enters the Earth. So the answer there is the magnetic North Pole, because we're talking about magnetic field lines. So it becomes your magnetic North Pole. So that's magnetic. Once again, if you just say North Pole here, it's not going to be right because we don't know which one you're talking about. But note magnetic field. So we're talking about magnetic north. And here we're talking about rotation. We're talking about geographic. So you have to specify that. State one advantage of the Earth's magnetosphere for life on Earth. Advantage, it protects us from solar winds. Protects us from solar winds. So that's what we have there. Right, we move on to the next question. If there are no questions here on number 2, we go to number 3. Number 3, 4 metallic bars suspended freely from a ceiling interact as shown in the diagram below. The points of attachment of X and Y on the ceiling are 4 centimeters apart. So here, the point where they are attached here is 4 centimeters apart, right? Then the two, they are moving apart and the centimeters there is 5. Right? Okay, the two bars in the middle are bar magnets. So these X and Y are bar magnets. And the distance between them is 5 centimeters. One of the bars, A or B, is made of iron and the other one is made of gold. So analyze the diagram nicely. All right, you can see A, it didn't move. X moved away. Y moved away. And B also moved. So B was supposed to be somewhere here, but it moved to the left, which shows kind of an attraction. So it means there should be a relationship here. All right? Okay, then we go to the next one, 3.1. Write down the term describing a material that is easily magnetized. Easily magnetized. So in the first question, they asked you to define ferromagnetic. Now here, they're asking you about something that, a material that is easily magnetized, right?
Magnetic materials.
Yes?
Magnetic materials.
Magnetic material or ferromagnetic material. Ferromagnetic material or magnetic material. That's correct. Okay, then we'll move on to the next one. It says, which one of the bars, A or B, is made of iron? A or B is made of iron.
B.
Right,
B.
but before we answer this,
B.
what are we going to say? Let's just analyze here. On the left-hand side of bar X on the magnet, this is north. It means here where it's not labeled here, this is south, right?
Yeah.
If this is south, therefore it means on magnet Y, this pole next to the arrow here, it's also south because they are repelling here. So south, south, all right? Then this one becomes north, all right? And this one is attached to this, it's being attracted to this north here. So the question says, which one of the bars, A or B, is made of iron? So the answer would be B because B is being attracted by the magnet here. So the answer is B. Clear?
Yes.
Right. Also checking there, so the answer is B. So your answer would be B. Then we move on to the next one. Determine the polarity of bar B closest to magnet Y. Right only, north or south? So like I said, I repeat again, on the left of X is north. So this empty space here is south. So this pole here is south. You move on to the next magnet Y. So if this is south, we see here there's repulsion because the magnets are moving apart. So therefore, this one is also south. On the right here of Y, this is north. So if this is north, B is being attracted by Y, right? So this is south. So this is south pole. So the answer here should be south pole. Clear? Right, we check again. The answer there, 9.3, is south. All right, then they need an explanation. The explanation, explain the answer to 3.3. We need to explain why are we saying south pole. All right, the explanation is here. All right, if this is north, that is south. And this is south. And this becomes north. There is an attraction, therefore, on B, this should be the south pole. Or you can explain magnet X repels south pole of Y, right? Magnet Y attracts B with the south pole because this end here is a north pole. So you can either do with the diagram or you can explain in words to explain what is happening there. Clear?
Yeah.
Right, okay. We'll move on to the next one. Sketch the magnetic field around bar magnet X, right? So your X, you've got your north and your south. So your magnetic field must move from north to south. So let's see how your diagram is supposed to look like, right? So your diagram looks like that, right? So you've got your magnetic field lines moving from north to south, right? Making sure no touching. So here I see there's some touching here. So this diagram is not 100% correct, right? So the marker location, it was 3 marks, all right, 3 marks. So mark number 1, correct direction of the field line. So if you point in the correct direction, you get a mark. That's 1. Shape of the magnetic field. So the shape of magnetic field, here it's going out, and here they are kind of oval shaped here from this end to that end. So you get a mark. So the general outline of the general look of the diagram, if it's correct, then you get that. Then next one, no field lines crossing each other. There's a mark for that, right? So like here, they are touching here. So in your diagram, you don't have to show them touching, all right? So it should be line by line. So for you to avoid touching, maybe make this bar a bit bigger so you've got space to draw enough lines on that one. No touching. So we check any line crossing, even at one point, then you lose this mark then, right? Okay, so that's 2.5. Then we move on to the next one. Sorry, it's 3.5, 3.5, sorry. Okay, 3.6, we'll move on to that one. It says, bars A and B are now removed. Bars A and B are now removed. So we are removing the iron and the gold. So this should be gold. So we are removing those two. We are left with only the 2 magnets, all right? Are now removed, and the points of attachment are now 2 centimeters as shown in the diagram. So we are going back to the original diagram. This was 4 centimeters. Now we are bringing them closer to 2 centimeters. So the question is saying, how will the change in the position of attachment affect the final distance of separation between the bars? Right, only greater than 5, less than 5, or remain the same? Right, so let's check here. Less than 5 centimeters would be the answer. All right. What is the reason? Magnitude of magnetic force is inversely proportional to the distance. B is no longer attracting to the right. So here we've got magnitude of the force is inversely proportional to the distance, right? Or you can say a decrease in the distance increases the magnetic force, B, and B is no longer attracting to the Y to the right. Okay, so that's what we have on 3.6 and 3.6.2, 21 and 22. That's what we have there. Less than 5 centimeters would be the answer. Reason being, the magnetic Magnitude of magnetic force is inversely proportional to the distance, and the B is also is no longer attracting, so the distance there will be affected. So the distance is affected on this one, yeah. Right, so that's what we have for 3.6.2. We move on
So,
to, yes.
what is, isn't it should be greater because the distance between the magnets are closer than before, therefore increases the magnetic field. Therefore, what is the magnets should be more further apart.
Um, Not exactly. Okay, not exactly greater. I would have gone, for example, with equal, because the force of repulsion between the two, since the magnetic field is still the same, would think that the magnetic field or the force here remains the same. If we bring them, then that means these two are supposed to be pushed further away. But remember, there was another element of pulling of dust. There was a B that was removed, right? So by removing B, it means Y is not going to go as far to the right as it would if there was a B, because it's being repelled and it's being attracted here. So because we no longer have a B, it should be less than. It should be less than, not greater than.
But so also, what is the distance between the magnets? At first was 4, now it's 2.
Yes.
So what is, shouldn't that affect your answer as well?
Remember, the magnitude of the force is still the same. The magnitude of the force is still the same. But here it's decreasing, reason being because of B. B is no longer there because B was going to stretch Y more to the right. But just reducing the 4 to the 2, still having, or because of the B is playing a role here in stretching this Y further. So because we have removed B, therefore it means this distance is going to be less. But if originally we didn't have A and B, then our answer was supposed to be remaining the same because the force is still the same. Remember, force is directly proportional to the bigger the magnetic field, then the bigger the distance, right? But because now the magnetic field is still the same, uh, the result would be, if we don't have A and B, then it means the magnetic force would remain the same. But because of the B was attracting this Y further, it would increase this distance than it was supposed to be if these two were not there. I don't know if it answers you.
Okay, so
Yeah. Look at B. B is the one that is stretching it, right? So when we remove B, because here I think the key here is this: A and B are now removed. A and B are now removed. Yeah. So these ones we need to take them into consideration here. So that's why on this answer here, they're saying the magnitude of the force is inversely proportional to the distance B. And B is no longer attracting Y to the right. So that distance there, instead of being a 5, if there was no B, maybe it was going to be 4 or 4,5. But because of the B, it's stretching it a bit further. Clear?
okay.
Okay. All right. Next one. We go to number 4. Two magnets are placed so that their north poles face each other. So you've got your north and north, which is repulsion. Explain the term magnetic field. Right. So for magnetic field, we have magnetic field is a region in space where another magnet or ferromagnetic substance can experience a magnetic force. A region in space where another magnet or ferromagnetic substance can experience a magnetic force. So that's the answer for magnetic field definition. Next one, 4.2, draw the magnetic field pattern between the two north poles of the magnets. North and north, the repel. So we expect some space here showing repulsion. So your diagram is going to look like this. So you're going to have your repulsion. No lines here, no magnetic field lines because of repulsion. Once again, your marker location, you've got one line. The first mark, lines are not touching. Always very important there. Right, then next one, the curved line. So there must be a space between here. The lines must be moving away from here, right? And the other one is direction. Since this one is north, north must always point towards the south. So they must be pointing away, not in towards north. So that's what you get for 3 marks. And then we move on to the next one. We have the next one. The graph below shows how the magnetic force varies with distance between the magnets. All right, so you've got your force and your distance. All right, you've got your force and your distance, and you get a hyperbola. The curve there is a hyperbola, is decreasing. So as distance increases, then your force decreases. So it's a hyperbola here, not a straight line, not directly proportional. Right, then 4.3.1, what is the mathematical relationship between magnetic force and the distance between the two magnets? Right, so we don't have a straight line, so it's not direct proportion, it's inverse proportion. So the answer there, what is the mathematical relationship? Magnetic force is inversely proportional to the distance between the two magnets. That's the relationship. All right, so magnetic force inversely proportional to the distance. All right, or you can just write it mathematically, magnetic force inversely proportional to the distance between the two. Right, we move on to the next one. 4.3.2, what is the magnitude of the magnetic force between the two magnets when they are 4 centimeters apart? So you go to your graph and use the 0.4 and join it to the graph. So you're gonna join to the graph, then you read the distance here. The distance here is 0.1. So when they are 4 centimeters apart, your answer is 0.1. So what is the magnitude of the magnetic force? The answer would be 0.1 newtons. Don't just say 0.1. You have to say 0.1 newtons. That would be the answer. Right, next one, 4.3.3. How far apart must the magnets be to experience a force of 0.05 newtons? How far apart to experience a force of 0.05 newtons? So you go to your graph, your scale here, 0.1, 0.2. So 0.05 is half of 0.1. So you're gonna go on your graph halfway between 0 and 0.1. You use your ruler to join a straight line that is going here on the graph here. All right. For me, it's going directly, I think, to 8. So your answer must be 8 centimeters. When you join a line halfway, yeah, you join it. All right, it's gonna go to 8. So your answer is 8 centimeters. So how far apart must the magnets be to experience a force of 0.05 newtons? The answer is 8 centimeters. All right. So that, according to this one, they're saying 10 here. But if you use a ruler, I think you get a better answer. 0.5, they're coming to a 10. So if you use a ruler, maybe you get an accurate one. For me, yeah, I'm just getting a 10. All right. Okay. But try it with your ruler. I think you've done it. Then you get a better answer. Okay. Next one. We move on to the next question. All right. It says, question number 5. A grade 10 learner performed an experiment to determine the direction and pattern of the magnetic field around a bar magnet. Based on the results, she drew the following diagram in which the north and south pole of the magnet are correctly labeled. All right, so the north and south are correct. Then they say 5.1, identify 3 mistakes that the learner made in the drawing. All right, what are the mistakes that were made here? What are the
Those
mistakes?
arrows at the end.
Come again?
Those arrows at the end. You see those arrows at the end of the north and the south? They're
Yeah.
both all going upwards, you know.
They're all going out. That's correct. Right. So your north is pointing outwards and your south is also pointing outwards. That's a mistake there. So they're supposed to leave north and they're supposed to enter south. So the direction here by the south pole end, they are supposed to be inwards, not outwards. That's one mistake. The next one?
Lines are crossing.
Lines are crossing, like here. Lines are crossing. The magnetic field lines are not supposed to cross. That's number 2. The last one,
Lines do not touch the magnet.
lines, they do not touch the poles here. These lines here, there's space here. All right, so this is incorrect here. So 3 marks for those 3 points. Next one, 5.1.2, name the device that the learner used to determine the direction of the magnetic field.
Compass.
What is it?
Compass.
Compass, correct. All right, so the device that you use is a compass. Next one, 5.1.3. The learner accidentally dropped the magnet and it broke into 2 pieces. Draw a sketch of the 2 pieces and label the resulting poles. All right, so for this one here, obviously when it drops a magnet, if I can just try to show you here, I didn't do the memo for this one. Share, let me just show you here. Okay. So if you draw your magnet here, this is your north. Right, you've got your north and you've got your south. You've got your south. If it breaks, it's going to break into 2 pieces. Right, so you're going to have 2 pieces here. Right, so you're going to have a smaller magnet here. My laptop is freezing here. Okay, you're going to have your north. This is the broken part. All right, then you've got another piece here. All right, then you've got your north. All right, so this is north, this would be north, and this part here would be south here. This would be your south. So this one becomes your south pole. This is your south, and this one is your north, and this is your south. So your diagram must roughly look like that. So that's what you're supposed to have there. Okay, right. Then we move on to the next one. Move on to the next one. Why is not showing here? Okay, I need this. Okay. Right. Next question. It says 5.1.3. We did that one. 5.2. People that are living near the North Pole of Earth can see northern lights, aurora borealis. It is a spectacular display of colored light in the sky. Briefly describe why it is visible near the geographical North Pole of the Earth and how it is formed. All right. That one, how did you explain this? Anyone?
So I said the northern lights are caused when charged particles from the solar wind reach the Earth's magnetosphere. They spiral along the magnetic field lines toward the north and south poles.
Okay.
And I wrote, the charged particles in the solar wind causes electrons in the atom to jump to higher energy states. When the electrons drop back to their lower energy states, they emit a photon of light.
All right, so there's emission of light, and the light that we see, because of the different energies that they have, then we're going to have different colors because of those excitements come up with different energies, and they tend to produce different lights of different wavelengths with different colors. Right, okay. So basically that's correct. I'll add the memo, then you'll compare what you guys have, but they sound correct. I think who's this? Zinedine, you just need to add more to that, the coloring part. Well, why do we have different colors there? No?
Oh, yes.
Okay, but I'll add, I will send the memo, then you guys will mark it and see what's not, what's missing. Okay, so that's what we have for the consolidation activity. Then we have got electrostatics. I don't know if there are any questions from the other guys there. Tepang, Zianda, Jolisha. I'm not sure who's this one with this long. I'm not sure who's this one.
Owen.
Owen. Okay, Owen. Any questions?
No, sir.
Okay.
No, sir.
Right. Fine.
Get Owen.
Okay. All right. Next time, Owen, you must write your name on your device so that we see your name here. Ne.
Okay, sir.
Okay.
Yes, sir.
All right. Fine. Let's move on to electrostatics. So I'm gonna send in the consolidation activity after this. Then you guys, you must do that. Wednesday we are moving on to electricity. Last topic for term 2. All right. And let me just reiterate here. In term 2, we only have June exams. So we've got paper 1 and paper 2 only. There is no practical in term 2. So at least with this, we are at an advantage because how are we going to do the experiment, right? So I hope in the other subjects you're doing the other tasks, but for us, it's just the June exam, paper 1 and paper 2. And from what I hear, they were saying they were gonna take out the term 2 activities since you have not been at school. So I don't know how far true is that. We hear when we go back to school, then we update you guys accordingly. If they're told we have to write an exam, I don't know. The school will tell us the way forward. Okay. Anyway, let's move on to electrostatics. Electrostatics, there was an activity there, and I did the memo. So let's just go over it. It says a glass rod is positively charged by rubbing it with fur. The fur is like wool, like cloth, like that. The rod is held near a neutral graphite-coated insulated sphere which hangs freely from a light cotton thread. 1.1, explain how the rod gains positive charge when it is rubbed with fur. Right, so the answer, fur rubs electrons off the glass. So remember that tribal electric charge series, right? You check which one is more positive, which one is more negative. So in this case, the fur is going to take electrons from the glass rod because the fur particles attract electrons more strongly than the molecules of glass do. So the rod has less electrons than protons. Therefore, it is positively charged. So electrons are removed from the rubbing. It means electrons are transferred from the glass rod to the fur. That's how it becomes positive. Next one. Draw diagrams to show the rod and the sphere when they are far apart from each other. So here your diagrams are going to be different here, but basic thing is when they are far apart, then this one will be positive, right? You can just show with your positive charges like here, shown electrons, right? Just showing with the dots. So when they are far apart, then this is what you observe here. Then the next one, B, the rod and the sphere when they are close together. So maybe to just take into consideration, the glass rod here is now positively charged and the sphere is neutral. So when you do your electrons, maybe you're going to be more specific like than what has been done here. Maybe you can show your positive here, and here you can show your positive and your negative. They are equal. They are equal. Yes, Poseto, you're asking?
No, sir, I'm fine.
Okay, so you raised your hand.
No,
Okay, all right, fine. So you've got your when you draw it, just show your positive here, and you've got your sphere must be neutral, so your positive must be equal with the electrons. Then when you go to B, when this comes closer, right, what are we gonna see? The sphere is gonna be attracted, so it moves towards this. So you can just show your polarization. By polarization, it means your positives, because the rod that is approaching is positive. So we expect your electrons to be near this end with the rod and your positive to be away. So you can just do that arrangement there. Then you go to the next one, the rod and the sphere, after they've touched each other and they've moved a small distance apart from each other. All right, so now they repel one another. So you're just showing now they've got the same charge because there was electron transfer that happened when they're in contact. Now they repel one another. because the charge on them is the same. So this depiction here just showing there was six. Now when this one comes here, we've got a 3, maybe a transfer took place. Then what we see a 4 and a 4. So the dots here, they are almost the same. So you can do the same with your pluses and your minuses, just to show the balancing there. Next one, 1.3. The fare becomes charged after it has rubbed the glass rod. What kind of charge does the fare gain? The fare is getting electrons, therefore it becomes negatively charged. Right? Where does this charge come from? Where does this charge come from? The fare gains electrons from the glass rod. So the charges are coming from the glass rod. Electrons are transferred to the fare from the glass rod. Right, next one, we've got about 3 minutes left. We just do this one, I think then we end it off. Please don't forget, we'll have again another lesson on Wednesday, same time. We'll hear also what the minister is going to say about us teachers going back to school later to this evening. You guys maybe are still packed at home for another month or a couple of days again. Right, this question is about spray painting a metal surface. An ordinary air spray gun sprays paint from a neutral nozzle. The nozzle of the electric spray gun is positively charged, and the object which is being coated with paint is earthed. All right, that is, it is neutral. Study the diagram. So you've got your diagram there. 2.1, explain what it means when we say the object is earthed. So earth means it is neutral, right? The object is connected by conducting wire to the earth so that it will always remain neutral. If it has an excess electrons, they will flow into the ground. If it lacks electrons, then electrons will move from the ground to that particular item, right? So that's what we mean by earth. Next one, in terms of electrostatics, explain how the electrostatic spray painting system works. The positively charged paint droplets repel each other as they leave the nozzle because like charges repel, right? Then the positively charged paint droplets are attracted to the earth object because they cause electrons from the earth to be attracted to the object. So opposite charges attract each other. So that's the explanation that we use. Right, I'll post this one as well so that you can mark. Then the last one, I will use this one is my last one. Give 2 advantages of using the electrostatic spray painting. Advantages of using something that is electrostatic than just no electrostatics. The paint sticks tightly to the object, right? So the paint is gonna stick tightly on the surface. The paint surrounds the object because its surface is oppositively charged. So paint is going to be attracted to the object. Very little paint is wasted, right? Because like charges, they repel, and like charges, they attract. So no paint is going to be blown away or is going to go another direction. Positive and negative will attract. So very little paint falls to the ground because it is attracted to the object. You don't need to move the nozzle around the object as much as you would have to do with other spray paints. And also another thing, when you paint your object, the painting becomes even. You don't have some points where you have more paint than the other one. Yes, Joshua, you raise your hand. Quickly,
could you go to the last question?
Yes?
The last question.
Yeah.
They were talking about charges. Were
Yeah.
they talking about positively or negatively charged? Because they would have said charge. Which object has more charge?
Which one?
The last question.
The last question. Basically, the rod was positive, so it was more positive.
No, like at the last question on the page.
On this
like
one?
Right at the bottom.
Or this one? I'm not sure.
No, more down. More down.